Okay, everyone, welcome back to the second part of the video lecture for Chapter 11. This will be the last video lecture for Chapter 11. Just need to wrap it up here. So you recall that in the first part of this lecture, we had talked about z-scores and how you calculate them, what they are. Remember that a z-score basically tells you, in terms of standard deviations, how far away from the mean a particular data point falls on the x-axis. So we calculate a z-score for a data point. It tells us that data point falls so-and-so standard deviations away from the mean. And remember that our formula for calculating the z-score is this. So z equals our x value minus the mean of the data set, mu, over the standard deviation, right? Okay. So up to this point, we've calculated a z-score, and then we use table B to find the area to the left of that. And remember, the importance of finding areas is that areas are probabilities on our normal curves, on our frequency distributions, okay? So if we can find an area, that tells us the probability of getting some value of x that falls within that particular part of the curve, okay? Areas are probabilities. And also remember that when we looked up a z-score in table B gives us the area to the left, but by subtracting that from 1.0 or 100%, we can turn that into the area to the right of that score on the x-axis, okay? Well, now we're going to start looking at how you find the area between two values, right? So let's say we have a z-score of 2.2. You look up that value on table B, it gives you this entire area to the left. Z-score of 1.4, you look up that value on table B, it gives you this area to the left. All right, now since 1.4 is a little closer to the mean than 2.2, this area here for 1.4 is going to be less than this area for a z-score of 2.2. So what if we want to find this area between these two z-scores? Well, if you know the area to the left of both of them, it's then just a matter of subtracting the smaller area from the larger area, and that would give you just this area here in between them, okay? All right, so let's take a look at an example of this. Blood cholesterol levels of men aged 55 to 64 are approximately normally distributed with a mean of 222 milligrams per deciliter and a standard deviation of 37, all right? So we have two questions here. What percent of middle-aged men have high cholesterol? That's defined as anything greater than 240 milligrams per deciliter. And then secondly, what percent have elevated cholesterol? That's defined as anything between 200 and 240. So here we're going to calculate an area between, okay? All right, so let's go ahead and calculate our z-scores. So remember, z is x minus mu over our standard deviation, so let's do that for 240 first. So z there is going to be 240 minus our mean of 222 over our standard deviation of 37. You work out that math, you end up with a z-score of 0.49, as you see right there. Second z-score, this is going to be for 200. So z equals 200 minus 222 over 37. That gives you a z-score of minus 0.59, which you see right here. Okay, so now we have our two z-scores. We've converted 240 and 200 into standard deviations, or at least their corresponding standard deviation on the x-axis. All right, so now we need to find the area to the left of 240 and the area to the left of 200. So let's do that. So if you look on table B, remember our first z-score here is 0.49. So here we have 0.4, and all the way over here we have 9, or 0.09, so 0.49. That gives us a z-score, let's call it 0.69, or 69%. That means that this area to the left of 240 is 69% of that curve, and that seems to be about right. That would mean also we have 31% to the right, okay? Now we have a second z-score of minus 0.59. Let's look that one up. So minus 0.59 right there. So that's a z-score of 0.2776. We'll call it 0.28, okay? That means, if we go back for a second, that the area left of 200 is 28% of our curve, and that seems to be about right just by eyeballing it, all right? Okay, so now we have our areas to the left from our table, but remember, our questions were what percent of middle-aged men have high cholesterol, so that's anything above 240, and what percent have elevated cholesterol, that's anything between 200 and 240. So we have areas to the left. Now we need to convert those to areas to the right because we're concerned about these cholesterol values above these points, okay? Above 240 and then again above 200. So for 240, our area to the left was 69%. That means the area to the right must be the remainder, or 31%. So 100% minus 69% is 31%. For 200 as a cholesterol value, area to the left was 28%. Area to the right must then be 72%. So here we see it. Area to the right of 200, 72%. Area to the right of 240, 31%, okay? So now we need to find the area between, and the way you do that is by taking the larger area, 72%, and subtracting the smaller area, 31%, from it. So what is the probability that x lies between 200 and 240? In other words, what is the area between 200 and 240? 0.72 minus 0.31, 41%, or 0.41 as a proportion, okay? That means that if you were to pick any random male, age 55 to 64, off the street and measure his blood cholesterol levels, you would see there's a 41% chance it would fall between these two values. All right? Okay. Next thing we're going to do is flip this calculation on its head. So up to this point, we've been given some value of x, like a cholesterol value, and we've been tasked with converting that to a z-score, and then from our table finding the area to the left and then possibly calculating the area to the right or the area between two z-scores. But we might also want to know the range of values that correspond to a given proportion or area under the curve. So here we're doing this backwards. We're basically saying, okay, we want to know, given this particular z-score, what is the standard deviation from that, okay? So we're looking at this backwards, essentially. So first of all, we have to find the area proportion in the body of the table, okay? And we're going to see how to do this here in an example. So let's say that we have 0.0125. So we want to know what z-score corresponds to an area of 1.25% on our curve. Well, you find 0.0125, z-score is minus 2.24. So we now know that that area to the left corresponds to a standard deviation of minus 2.24. In other words, a standard deviation that is that's 2.24 standard deviations left to the left or below our mean. Okay, let's look at an example to make this more clear. So first of all, we're going to have to rearrange our formula here. So for z-score, we're calculating for z, right? We're solving for z. But in this case, we're going to be solving for x. So that's what the inverse normal calculation is. You're not solving for z, you're solving for x. And for some reason, it didn't fill in my formula down here, but I'll fill that in here in just a minute, okay? So let's look at this example. The hatching weights of commercial chickens can be modeled accurately using a normal distribution with a mean of 45 grams and a standard deviation of 4 grams. Again, these are hatching weights. So what is the third quartile of the distribution of hatching weights? Okay, what's the quartile? Remember we talked about the 5-number summary in the box plot, right? You have the minimum value, the first so going from the bottom to top, you have the minimum value, first quartile, the median value, the third quartile, and then the maximum value. The first quartile is the point where 25% of the data lies below it. The third quartile is the point where 75% of the data lies below it. So the third quartile is the 75th percentile. You have to recognize that, okay? All right, so we know our mean, we know our standard deviation, and we're going to figure out the area, or we'll know the area under the curve, okay? We want to find x. We want to find the hatching weight that corresponds to that particular z-score. All right, so let's go forward for a second. We have to find the 75th percentile. So we've got to find the point in the table that represents 75% of the area being to the left. So you find 0.75. Well, notice that we don't have 0.75. We have 0.7486 and 0.7517. When this is the case, when the actual value you want lies between two numbers, you always select the lower number on the table. It's just convention. It's a more conservative way to do it, all right? So we're going to pick 0.7486. That's a z-score of 0.67. 0.67. So let's go back for a sec, all right? So now we know we have a z-score of 0.67 for our 75th percentile, okay? All right, so table B gives the area to the left of z. So we looked for the lower 75%. We found that was a z-score of 0.67. So remember our formula for z-score, let me fill this in, was x minus mu over our standard deviation, right? And we want to rearrange that to calculate for x. So x then, if you rearrange this algebraically, x then equals mu, our mean, plus our z-score times our standard deviation, all right? So we know that our mean is 45 grams, and we're going to add to that the product of our z-score, 0.67, times our standard deviation of 4. And that equals a hatching weight of 47.68 grams. All right, 47.68 grams, or call it 47.7 if you want. That means that the 75th percentile is 47.7 grams. 75% of hatching weights fall below that. That would also then mean that 25% of hatching weights lie above it, okay? All right, let's look at another example here. All right, blood cholesterol levels again. Men age 55 to 64. We have a normal distribution, a mean of 222 milligrams per deciliter, and a standard deviation of 37 milligrams per deciliter. So question is, what range of values corresponds to the 10% highest cholesterol levels? Okay, 10% highest. All right, so again, we're calculating for x here. So if it's asking for the 10% highest, we have to find the z-score that represents the 90th percentile. 10% above that, 90% below it, okay? All right, keep in mind, because it says 10% highest, we're going to be asking about, or interested in knowing, something about the area to the right of that point on that x-axis. Okay, so we're going to go to our table here, and we're going to look up 90%, or 0.9. So closest we have is 0.8997. So our z-score then is 1.28. 1.28. Let's go back. All right, 1.28. We have our formula here for calculating x. So our mean is 222. We have a z-score of 1.28 multiplied by our standard deviation, right, of 37. Add 222 to that product, and you get 269.4. 269.4. So that would fall probably right about there, and that means that the area to the left of that should be 90%, and then we're concerned about the area to the right, which should be 10%. So 269.4 represents the cutoff between area to the left 90%, area to the right 10%. So the question was, what range of values correspond to the 10% highest cholesterol level, right? So we found 269.4, so greater than 269 would be the answer, okay? All right. Now, last part of this chapter has to do with another way to assess whether or not a data set is normally distributed. In earlier chapters, if you recall, we talked about using dot plots or stem and leaf plots, or more commonly, using histograms to look at the overall distribution of the data to get an idea of whether or not the data is skewed, if we have outliers, that kind of thing. Another way to do it is through what's called the normal quantile plot. Okay, and this is a relatively common way of doing this, but again, you want to assess whether or not your data set is normally distributed before you try and calculate z-scores and look at areas and that sort of thing. So what happens here with a normal quantile plot, and keep in mind that Minitab is going to do this behind the scenes for you. You won't have to do this by hand. What's going on here is that the data points are going to be ranked, usually from lowest to highest, and the percentile ranks are converted to z-scores. So we rank our data points in order, and we convert those to percentile ranks, and then based on that, we convert those data points to z-scores. The z-scores are then used for the x-axis, and the actual data points in our data set are used for the y-axis. So what we get is basically a scatter plot, okay? So if the data is normally distributed, we'll have basically a straight line pattern in our scatter plot. So let's take a look. So here we have our z-scores for our data on the x-axis and the actual data points in terms of, in this case, rain pH value on the y-axis. And you see we have a relatively straight line there. That's an indication that you would have a normal distribution if you did the density curve for this, or if you looked at it in terms of a frequency distribution, a histogram. What if it's skewed? Well, if it's skewed, you're going to have a curved sort of line or distribution of those points in that scatter plot, okay? And so notice how here, up to this point, you have all your data points fairly close together. Here they spread out. That's an indication of right skew. So in this case, you'd have a curve that might look something like that, with the tail coming off to the right, okay? If you had left skew, you'd have few data points down here that were widely spaced, and then closely spaced data points on the rest of the curve. That would be an indication of left skew. So if you do a normal quantile plot, you get a straight line, something like this, then you have a normal distribution. If you get a curved line like this, or it could be you know, curved that way, for example, that would also be an indication that you have a non-normal distribution. All right, and I think that Minitab is going to, Minitab will do this for you. I think your homework number 3 will actually require you to do one of these plots, or maybe it's a later homework, but you'll have to do one. But it's real simple to do in Minitab, and it's just another good way to sort of check and make sure that your data set is normally distributed, okay? All right, so I think that wraps it up then for chapter 11.